Hi, I'm Shuqing Chen from Goodix, Optic BU. In the past 7 years, our team has been focusing on the research field of health biosensors. Under the background of hard trend of digital health, more accurate, more portable, and lower power consumption measurement of vital signs has always been our pursuit of innovation. We hope that those innovation efforts can provide more value for sensor product engineers. Today, Goodix owns PPG-based heart rate, HRV, and SpO2 measurement, ECG measurement, bioimpedance-based body composition analysis, electrodermal activity, and respiration measurement. This video will introduce how Goodix health biosensor help designers mitigate the challenge they face today. First, let's start with PPG.
With the rise of smart wearable device, continuous heart rate measurement has become an essential function, which brings great experience to users for fitness and wellness. Its measurement principle is based on PPG technology. Specifically, the pulse causes periodic systole and diastole of the artery, causing change in blood volume. By using LED light to irradiate the skin to the tissues and detecting change in light absorption using a photodiode, pulse wave information can be captured. The absorption of light by most human tissues is basically constant, which constitutes the DC component of PPG. Since the volume of blood in the artery changes periodically with the contraction and relaxation, the absorption of light also changes accordingly, which constitutes the AC component of PPG. The ratio of AC to DC is called perfusion index, which is the most basic indicator for measure the quality of PPG signal. Usually, the transmittance PI can reach the 0.2% to 10%, but the reflective PI applied to the waist is usually much weaker than the transmittance type, so the measurement is more difficult. Another important parameter is CTR, which is a design value that measures the ratio of the receiving current of PD to the driving current of the LED. It's affected by LED's luminous efficiency, the PD's quantity efficiency, and the distance between LED and PD. Generally speaking, the higher the CTR design, the higher conversion efficiency, which is helpful for the measurement performance and reducing power consumption. To obtain the best PPG signal, the wavelength of 530 nanometer is currently selected as the light source of PPG heart rate measurement. This is a typical PPG signal waveform after filtering. The pulse wave cycle is what we usually call the heart rate. The unit is BPM, which is the number of pulse waves per minute. The heart rate can be calculated by counting P wave per minute in the time domain, or by using FFT to obtain the result from the frequency domain. Through the pulse waveform, we can further obtain the time fraction between the pulse, which we call heart rate variability, and the unit is milliseconds. It's obtained through statistics in the time domain. Common statistics include SDNN, RMS-SD, and PNN50. HRV can reflect your mental state very well. When you're tired, anxious, or irritable, your heart rate is usually low at this time. We can increase HRV by adjusting breathing or meditation, which can activate the prefrontal cortex and increase HRV. That helps our body and mind adjust from a state of stress to a state of self-control and better meet challenge. During the outbreak of the COVID-19, People's awareness of the importance of blood oxygen saturation has been enhanced. Blood oxygen saturation refers to the ratio of oxyhemoglobin to total hemoglobin in the blood. The normal range is 95 to 100%. When the oxygen supply in the blood is insufficient, this ratio will drop. It's an important physiologic parameter of the breath cycle and can help people understand their own health status. Daily use of non-invasive blood oxygen measurement is also based on the PPG principle. Compared with heart rate measurement, blood oxygen measurement requires the use of two colors of lights, red and infrared light PPG signals. From the absorption spectrum of oxyhemoglobin and reduced hemoglobin in the picture, we know in the red light 600 to 700 nanometer band, their absorption difference is the largest. However, the difference in absorption in the range of 800 to 1000 nanometer in the infrared spectrum is small. Using wearable rule, the AC and DC amount of the red and infrared light are measured respectively. Finally, the blood oxygen saturation is obtained by calibrating and fitting A, B, and C. In engineering implementation, 660 nanometer and 940 nanometer are often used. Also, PPG is a relatively mature technology, but the accuracy on smart wearable device has always been unsatisfactory. And there are also limitations on power consumption. Improving accuracy has always been the goal pursued by engineers. The specific challenge includes the difference in PPG signal among different populations mainly comes from the difference in skin tone, difference in tissue thickness, and difference in user preference of tiniest of value. The DC amount of different light source varies greatly due to the difference in the depth of light penetration through the screen at different wavelengths. That can cause a large difference in the optical path in west reflected measurement, which in turn leads to a large fitting dispersion, making it easy to obtain false oxygen measurement results. The ambient light changes greatly. In different environments, in daily use scenarios, the ambient light will fluctuate greatly as the user moves to different locations. Motion artifact is also the most difficult point that affects the accuracy of PPG in Westbound wearables. There are many related research topics. The scenario of users' daily activity are complex, and the frequency range is wide, including the most difficult to handle core frequency interference. AFE is one of the key factors affecting the accuracy of PPG measurement. Goodix high-performance PPG receiving channel has balanced power consumption and performance. Extremely low input ripple noise challenges the accuracy of heart rate and blood oxygen measurement under the limited PI. Extremely high SNR allows more flexible choice between signal quality and LED driving. Super strong ambient light and DC cancel capability ensure that the TIA can work in optimized performance even under complex and changing ambient light conditions. The built-in AGC preprocessing module eliminates the gain error in reception, calculates signal values at different gains accurately. Next is the rich AFE optical transceiver channels. For driving, the latest GH3300 and 3030 series product support up to 16 LED, which can drive the 4 channels simultaneously, with 200 mA maximal single-channel driving capability. For receiving, up to 8 PD and 4 independent RX channels are supported, allowing synchronous sampling to reduce the LED power consumption. 32 sampling time slots are supported, enabling more diverse sampling timing control. Those results provide the engineer with more flexible optical design solution to mitigate the motion artifact impact and improve accuracy for motion heart rate and west blood oxygen measurement. You can refer to Goodix related guideline for more information on the principle of optical design. Our Magellan 1 and the latest Magellan 2 demo watch adopt a design using alternating LED and PD location. And based on this, we have developed and optimized our heart rate and blood oxygen algorithm. The figure shows the performance on the different channels and the performance comparison after multi-channel fusion. In addition to provide the leading AFE, Goodix also offers the VSM algorithm product. Deep learning models are adopted for both the heart rate and the SpO2 algorithm, which have stronger fitting ability and higher prediction accuracy compared to traditional feature extraction. SpO2 algorithm, for instance, first, noise reduction and other pre-processing are applied to the input data. Then, models such as CNN or RNN are used for feature extraction. Features can be different skin tones, different ambient light intensities, different motion states, and more. Using training model, the model parameters are then adjusted based on the validation set to obtain the final heart rate and SpO2 values. Goodix VSM algorithm have been widely used in many smart wearable devices, helping customers to quickly bring the product to market with performance higher than industry average level. At the same time, we are still continuously optimizing our algorithm to unleash the full potential of AFE.
Next, let's go to ECG.
An electrocardiogram is a recording the heart electrical activity, so rapid cardiac. It reflects the rhythm of the heart. If two electricity are placed on either side of the heart, small voltage change between the two electricities during the depolarization can be captured. A healthy heart cardiac cycle. Depolarization occurs from the right atrium to the left atrium, forming a P wave on the ECG. The QRS wave group reflects the rapid depolarization process of the ventricle. The T wave represents the rapid repolarization process of the ventricle. It can be categorized by leads, which essentially means observing change in the electrical current of the heart from different angles. This is a diagram of 12-lead ECG, which can record the potential change of 12 sets of leads on the body surface simultaneously. It consists by 3 limb leads, 3 augmented limb leads, and 6 percordial leads. In daily wearable device, such as ECG patch and smartwatch, the simplest single-end ECG is popular, which can be used to detect atrial fibrillation. This is the most basic single-lead ECG detection circuit, which consists of 3 electrodes. The left arm and right arm electrode form a differential signal. After amplifier, high-pass filter, and ADC to obtain the final digital signal. The other electrode is the right leg, which provides a low-impedance reference point to the human body to improve the anti-interference ability. However, when the coupling path is small, such as in ECG patch, this electrode can be saved to simplify the design. In actual measurement, the resistance of the electrode on the human body has a significant impact on the measurement result. So we must have an understanding of the electrode. This is a simplified circuit model of the electrode and its contact with the human body. We can regard the human body as 2 parts. One is the trunk of our body. The other part is the striatum column that contacts the electrode and can be equivalent to an RC parallel network. It's affected by the dryness of the skin. The contact between the electrode and the human body can form a half cell due to the difference in ion activity. And the contact can be different for a wet electrode and a dry electrode. The wet electrode is applied with conductive gel and can reduce the contact impedance with the skin, while the dry electrode is in direct contact, and the contact impedance fluctuates greatly. All of this makes the real ECG signal noise compared to the ideal signals. The noise comes from baseline drop. It's caused by change in respiratory impedance and is about 15% of the ECG amplitude. It's mainly below 0.5 Hz. Power line noise. The test subject is exposed to radiation from the surrounding power grid, which can couple power frequency common mode interference with a voltage of several volts to a dozen watts. The challenge of measuring ECG on a watch lies in the fact that the electrodes are on the wrist and finger respectively, and the contact impedance and parasitic capacitance of the electrode will differ, transforming common mode interference to differential signal and forming strong interference. EMG noise. It comes from a muscle contraction other than the cardiac muscle, and is about 10% of the ECG amplitude. Especially during exercise, the interference will further increase, and it mainly causes high-frequency noise. Motion artifact. Due to the movement of the test subject, the contact impedance between the skin and the electrode change results in the charge distribution under the polarization voltage changes, resulting in low-frequency voltage inflections. Its amplitude is much lower than ECG signal itself. Our solution to those challenges include the input impedance is greater than 10 gigaohm, which can greatly reduce the signal error and the motion artifact caused by the impedance reflection of the dry electricity, up to 1.3 volt input range, which can easily adapt to the polarization voltage. 110 dB CMRR. The IC also supports active shading, which helps to reduce the parasitic capacitance of the input line to the ground. Greatly reduced the CMRR decline caused by impedance of the differential input. Support AC and DC dual modes. Engineers don't need to trade off motion artifact and ECG waveform quality. Low power consumption at 500 Hz sample rate. DC mode is 588 microamp, and AC mode is only need 280 microamp. Integrated lossless compression IP, 30% compression ratio, which can greatly reduce the power consumption for data transmission. The IQ demodulation for lead-off detection. Compared with the traditional threshold detection method, it can adapt to more complex and variable impedance change. At the same time, our latest product also supports the leading detection with an external buffer. The original intention of our design is to continuously monitor the heart in a more portable way, so as to help users better take care of their health. Our unique points include support 1.2 volt low power supply, 96 kilobyte FIFO. There are more choice between real-time and low power. Those details are all for the pursuit of long monitoring time. In addition to single-lead ECG application in wearable device, Goodix health product can cover the following functions right now: 1-lead ECG and respiration monitoring, 3-lead detection, and 5-lead detection.
Next, let's go to EDA application.
Impedance refers to the ratio of the voltage to the current. It consists of the two parts, resistance and reactance. We can excite a current with a specified amplitude and frequency on a DOT, and then measure the voltage. To measure the impedance, we can obtain the impedance spectral information of the DOT according to different excitation frequencies, so as to completely solve the equivalent circuit mode of the DOT. But it should be noted that the equivalent circuit is not unique. In an actual measurement, there are 2-terminals and 4-terminal methods. The 2-terminal method refers to the excitation source and the measurement channel shell electrodes, while the 4-terminal method separates the two channels. The 2-terminal method features the simple connection. However, the measured impedance includes the contact impedance in addition to the DOT. When the contact impedance is comparable to the DOT, the error will be non-negligible. So this method is more suitable for measurement equipment with small contact impedance, or the absolute value is not required. The four-terminal methods can solve the error caused by contact impedance because there is no excitation source in the measurement path. However, the four-terminal method also has a problem in the actual use. It can be seen that when there is a parasitic capacitance in the excitation electrode, the excitation current can discharge part of the current through the parasitic capacitance. So the current flow into the DOT is not equal to the excitation source current anymore. In addition, the current that should not appear at the receiving end will also cause the leakage current due to the existence of the parasitic capacitance of the receiving electrode, so that the measured voltage is not equal to the voltage across the DOT. So, parasitic capacitance constitutes a significant source of error for tripolar impedance measurement. The error between the excitation current and the actual current that falls on the DOT due to the parasitic capacitance of the excitation source can be solved by calibration, specifically including offset and freeze calibration. Offset comes from DC BIOS and is a fixed amount that can be directly subtracted. Freeze offset comes from capacitance. Next, let's take a look at the effect of parasitic capacitance on the receiving end. In practical applications, capacitance is inevitably present between the electrode and the ground, including capacitance on the PCB trace, parasitic capacitance on IC and electrodes, and the capacitance on smart wearable device range from about 5 picofarad to 20 picofarad. And the reactance at 50 kHz is in range of 160 kilo to 640 kilo ohm. In the GH3300, the input impedance is much greater than the impedance caused by parasitic capacitance. So we can simplify the input impedance as the reactance of the parasitic capacitance. We usually adopt dry electricities for impedance measurement, whose contact impedance may vary in a wide range. Here, we can also use the equivalent circuit of dry electricities introduced previously. The parasitic capacitance determines the input impedance. Large capacitance means smaller input impedance. The fraction of the contact impedance will be reflected in the measurement error, which is difficult to be calibrated. The error can be ranged from 0.16% to 12.5%. Furthermore, when the input impedance at both ends of the DOT is unbalanced, which will worsen CMRR and increase potential interference error source. Therefore, when the change in contact impedance is inevitable, reducing parasitic capacitance becomes the key to improving system performance. There are two ways to reduce the impact of parasitic capacitance. First, reduce the parasitic capacitance as much as possible by shorting and high impedance PCB trace. The second way is to reduce the charge through the capacitor. This can be achieved by active shading. Change the reference to the active shading instead of the system ground. In addition, we can use a compensation capacitor to compensate for the leakage current of parasitic capacitance, thereby reducing errors. The GH3300 series support a maximal single-end 50 picofarad compensation capability, helping designers deal with the parasitic effects. After calibration, our impedance measurement solution can achieve an impedance measurement accuracy of 0.1% and a freeze accuracy of 0.1 degree. After introducing the principle of impedance measurement technology and our solution, let's take a look at the application on human bodies. First of all, let's start with the basic composition of the human body. The human body is composed by fat, protein, minerals, and water. Since fat is non-conductive, we can divide the human body into two parts, fat mass, and fat-free mass. With such known information as weight and height, we can treat the human body as an object with impedance to be measured. Since conductivity is related to fat-free mass, we can perform impedance measurement to calculate the FFM, thereby measuring the body fat percentage. Furthermore, fat-free composition contains many substances. Can we distinguish the accurate FFM? The answer is yes. Let's take water content measurement as an example. This is what cells suspended in body fluids look like. The cell membrane separates intracellular fluids and extracellular fluids, both of which are liquid containing electrolytes and can be regarded as two conductors with a certain resistance. The liquid bilayer structure of the cell membrane is similar to a plate capacitor, and the equivalent circuit is like this. When low-frequency current passes through the human tissue, the capacitor is equivalent to be insulated, and the current seems to bypass the cell. When high-frequency current passes through the human tissue, the capacitance of the capacitor decreases, and the current can directly pass through the cell. In this way, we can use different excitation frequencies to measure the composition of intracellular and extracellular fluids. Enhanced by the bioimpedance measurement technology, Goodix offers rich sets of products. In addition to the 4-electrode GH3300, we also launched the 8-electrode GH3400 and GH3500 for more accurate whole-body composition analysis. The GH3500 even integrates 3-lead ECG for measurement, greatly expanding the function. In addition to ensuring the basic impedance measurement accuracy, we have the following advantage for human body composition analysis. Wide range of excitation frequency from 1 kilo to 1 MHz, providing a wider range for impedance spectral analysis. Support impedance measurement at up to 130 kilo-ohm, better covering the impact of dry electricities. 470 microamp power consumption for measurement. Integrated codec engine, directly providing amplitude and phase information, reducing the requirement of MCU. Support switching between excitation and receiving channels, allowing more flexible whole-body composition analysis. Next, we introduced another important application, electrodermal activity, also known as galvanic skin response. Back to 1849, German Dober's Raymond first discovered that human skin has electrical activity. Later, science further discovered it is autonomously regulated by sympathetic nerve activity, which drives human emotional states at the subconscious level. Therefore, skin conductance allows direct measurement of autonomous emotional regulation. Essentially, EDA is to measure the change in the body surface resistance of the human body. This is the equivalent circuit model of the skin. We can use a two-terminal impedance measurement method to monitor the EDA signal. In EDA testing, focus on two indicators, SCL and SCR. SCL refers to the baseline level of skin conductance and can be used as a baseline in EDA testing. SCR refers to the skin conductance response. When stimulation happens, there is a delay time, usually 1 to 5 seconds. Then there is the rise time, and the GSR will reach its peak amplitude. The rise time reflects the response to the stimulus of an individual. Finally, there is the recovery time, during which GSR returns to the baseline level. EDA measurement is also subject to motion artifact interference, just like ECG. Based on the data collected by our demo, our experiments also prove that meditation or slow breathing can effectively reduce the SCL, but we have to accept the unsettling fact. The EDA corresponding to the west, which is the best continuous monitoring position, is not ideal, while the relatively ideal position is on the palms or fingers. Considering this characteristic, we combine the form of our Magellan 2 watch in the design to support the finger-active tests like ECG and BIA. Also, a continuously monitoring that supports the west position like PPG to meet different application scenarios.
After long-term accumulation, Goodix now has a very rich product portfolio to meet the needs of different customers. Well, we provide the total solution including hardware, optical design, and algorithm to facilitate customers to achieve product launch more quickly.
Currently, our products are widely used in various applications, including smart wearable device, body fat scales, wireless patch, Holter, multi-parameter monitors, and blood oxygen clips. Among them, GH3220 and GH3020 as our star products have helped engineers achieve the high-performance heart rate SpO2 and ECG measurement on smartwatch, allowing tens of millions of users to better monitor the health data in daily life. The newly launched GH3300 and 3030 further enhance the performance with low power consumption than the previous generation. The added EDA detection function allows monitoring in motion. GH3400 is dedicated to helping engineers with extremely high requirements for human body composition analysis performance to solve accuracy problems in practical design. GH3500 supports monitoring ECG during body fat measurement, giving product manager more imagination. GH7000 is a high-performance and low-power product series developed for clinical ECG monitoring. Goodix also provides an optical module, GH3011, with integrated PD solution. It can help customers achieve high-precision SpO2 measurement below 0.2% PI in blood oxygen clip applications. Now, we have provided a complete introduction of the function and application of Goodix Health biosensors. Engineers can apply for the related evaluation kit on Goodix official website or contact our district to purchase. We not only provide the leading IC, but also feature flexible business model to help customers for total solutions. For customers who already have optic and algorithm development capabilities, we provide the complete SDK and basic design guidelines. For customers who focused on other functions of smart wearable but have not accumulated much experience in the field of health sensing, we can provide the Goodix proprietary optical modeling and simulation models as well as VSM algorithm to help customers with optical design. Moreover, we actively cooperate with third-party application algorithm companies to achieve complete optimization and integration from bottom-level drivers to upper-level applications, helping customers enrich the fitness and wellness function and enhance the product value.
The above is the whole content of this video. If our products can meet your needs, please contact us through the following ways. Thank you for watching.